Good afternoon. Welcome to the CFAIR webinar on Big Data, Background and Applications Used in Agriculture and Food Systems. I'm Jane Kolodinsky, and I'm the CFAIR Program Chair and currently Professor at the University of Vermont. As of January 1st, I will be Dean of the Business School at Western Colorado University. It is my pleasure to be moderating today's webinar. It's CFAIR's mission to translate high-level research and knowledge to a diverse audience that includes policymakers, elected officials, and federal administrators. When we demonstrate the value of the profession to these groups, the Council increases public appreciation for research, extension, outreach, and academic programs in agricultural and applied economics. Before we get started, I want to provide some background on today's topic. Volume, velocity, variety, and veracity are descriptors of big data. Remote sensing, geospatial, census, and supermarket scanner data are only a few examples of big data. Accessibility, quality, and security are challenges associated with these data. Higher yields and better matching of product to consumer demand are two outcomes from research using big data. To learn more about big data and how they can be used for decision-making and policy, that's what we're talking about today. We'll provide you with some background and two applied examples. CFAIR has assembled a panel of experts to discuss their work, starting with Dr. Keith Coble. Keith serves as Vice President of the Division of Agriculture, Forestry, and Veterinary Medicine, DAFVM, at Mississippi State University. The division is central to MSU's long-standing land-grant mission of research, teaching, and service. Coble obtained his PhD in agricultural economics from Texas A&M University in 1993. Meha Jain is an associate professor of geospatial data sciences and food systems at the University of Michigan in the School for Environment and Sustainability. Her research examines the impacts of environmental change on agricultural production and strategies that farmers may adopt to reduce negative impacts. Yuqing Zhang is the H.B. Price Professor at the Department of Agricultural Economics, University of Kentucky. Dr. Zhang's research focuses on food marketing, policy, labeling and certification, big data, with implications for safety and health. He has published widely in journals such as the American Journal of Agricultural Economics, Health Economics, Regional Science, and Urban Economics. Before we start, we wanted to explain how to ask questions during the webinar to make sure that you, the audience, knows how to engage. During the webinar, you can put questions to one or all of the speakers by typing into the box in the control display, accessed by clicking on the question drop-down as shown in the slide. There we go, there's the question drop-down menu, and sending it to the organizer. You type your question in and then hit send. Now I'll hand the webinar over to Keith, who will start us off. Welcome, Keith.
Hello. It's good to join you today and to talk about this issue. Jane and I were talking before I began that this continues to be a topic that attracts a lot of attention, and hopefully we can provide some clarity today. If you will scroll forward. One of the things that I find fascinating as an economist is that data often has public good attributes. And if there are non-economists on the call today, a public good is something that all of us may be able to use. And our common examples are parks and things like that. The key thing about data is that I may have a data set that has value for one purpose and use it for that. and may need my data set for something else entirely. And the fact that I used it for my need does not diminish it. It's the potential use by somebody else. And so ultimately, data has a high cost to produce in many cases. And one of the things that I think what is going on in the world today is that we're finding that the cost of producing data with sensors and technology has diminished. But ultimately, there are still data sets that are very expensive to produce. I think of some of the things like the USDA ARS produce data sets that are extremely costly to produce, but they're valuable and many people can use them. And one of the things, Jim Verkaman was an editor of the American Journal of Ag Economics many years ago. And he made a comment at a conference that I was at where he said that as an editor and he saw the submissions coming in, he knew that in many ways, the submissions that he received were driven by data availability rather than the relevance of the question. And I've long believed that Jim was right about that. So the lack of data or the potential new availability of data is going to drive our research agendas. And I think that's important, and thus we need to have greater data availability. January use this terminology. I've seen others describe 5 V's or 3 V's, but when we wrote the paper for the AEPP a few years ago, we settled on 4 V's related to data. Volume, huge amount of data being generated, and also velocity of that data in terms of if we have sensors and we have technology, it changes the need that we have to be able to manage just the sheer volume of data that is coming at you in real time. We also are living in a world where there is a huge variety in terms of the data that we get, sensors on equipment, controllers, RFID tags, and drone imagery, and we could go on and on and on as if we think in the ag and food sector, we can think about not only at the farm level, which I've kind of focused on, but all through the supply chain and to the consumer. Is there data? Can we validate certain things with data that follows from the farm to the consumer along the way? And finally, we talk about veracity, because data quality is an important issue. Almost invariably, both sensors and human error influence the quality of ag data. We will get perhaps more data than it has merit, but being able to sort accurate data versus inaccurate data is an important point. Years ago, I met with a company that specialized in cleaning data sets. That's all they do, and is probably a great business model today. Next slide. Years ago, CFAIR asked a group of us to write an article, and you see the names of the co-authors on here. There's a lot of things that we can talk about where big data touches our profession. We can begin with precision agriculture on the farm, the inputs, the yield monitors, for example. Another thing are government sources of data, such as weather and satellite and soil maps. Many years ago, I talked to the founders of a company called Climate Corp, which was bought by Monsanto and then became a part of the Bayer system. And they really the whole genesis of what they did there began with them looking at data sets that USDA had provided and ultimately made freely available to anybody who wanted to download those data sets, and generated a lot of research potential applications on farms, and also other opportunities to use it in a novel way. I already touched on the supply chain issue of traceability through the supply chain for food safety purposes, sustainability verification. With each year, I think that becomes a greater need to generate data along the way as we figure out how to do that in food systems and other systems as well, to evaluate supply chain efficiency that we've looked at a lot since the COVID data that came along. And then consumer demand data, which is perhaps of all the things that I've discussed, the one that has been around the longest within the profession. And so I think that continues to be a very important area, and along with that, social media data as well. Next slide, please. I just talked about Climate Corp. This is one of the things that got them started. And if you think about ultimately the background behind this map is USDA spending years testing soil for soil type and elevation and other factors as well, that ultimately led to this map. And that this map has been used in all over the country, obviously, and also for a lot of different applications along the way. I've seen it posited as sources of adjustments in crop insurance rates. I've seen it used for a lot of other purposes as well. And so I don't think we should forget about when something like this is created in the public space and made publicly available, it has a huge potential to impact the entire sector. Next slide, please. I think one of the real challenges, it's really not very hard to get your hands on a lot of big ag data. You know, we can have planter data, soil type, planting populations, fertilizer, weather, yields, and other inputs on millions of acres. One of the things that I caution people is that this data that is being generated in production agriculture, as it's being produced by the supply chain, is not a randomized design. There is bad data in the process. There is selection bias because you're almost never going to get all of the data that is out there. One of the cautions that I generally give people is that the data that is being generated in this way is really for a very specific purpose. And one of the things that we need to understand is that there is still enormous value to randomized controlled data collection, surveys. I really question, some will suggest that the yield monitor data could replace the NASS surveys of farms. I think ultimately there's still enormous value in using randomized control surveys as a ground truthing for a lot of this data that is being generated, because it's not from an experimental design. But we can learn from it, and I think there are billions of dollars being invested today in learning from this data. But it's going to be very complex as you put all these factors together. And therefore, some people have expressed disappointment that we haven't moved ahead further than we have in these applications. But I think we've often underestimated the complexity of some of the situations that we're analyzing. Next slide, please. one of the things when I've talked to lawyers about this issue, they say the real issue is about data access. It's not about ownership, although a lot of people talk in terms of ownership. The reality is that I have an iPhone, a lot of you have an iPhone, and when we signed that contract, when we got our iPhone that we did not read, we gave the company access to information. And that same is true when you buy a tractor or a yield monitor or something like that on a combine. And ultimately, I think we need to start talking in terms of trust and relationships in terms of having access to data. And I think this has been one of the challenges with farm level data is that the collection of data by government is often discouraged by people who are afraid of how it might be used. And for those of us in academia, I think we have to understand that we run a risk of when we ask people for data that we have got to have a relationship with them. We have to, in many cases, I think, provide assurances that we will not use this in such a way that will come back to haunt that individual. Years and years ago, I did my dissertation, though at Texas A&M, I used on-farm data from the Kansas Farm Management Record System, which existed then and to this day. And the situation there is that there's a certain amount of trust and necessity for there to be trust because one incident where data is shared and it's used against an owner, that is a story that would run through farm communities like wildfire and destroy the ability of other researchers to have access to data. I really believe where we are likely headed in the future with the large volume of data and the security needs to assure trust, I think the day is coming where we as researchers are going to go to an enclave and we're going to do analysis inside that enclave and only take away the results of our analysis. I've actually done that. I've used the NAS enclave to have access to certain data. NAS and the ERS are doing this now, but I think increasingly because of the quantity of the data and the trust region, we're rather than attaching data sets to emails, we're going to be doing our analysis inside enclaves for security. Next slide, please. Some cautions real quickly. I think one of the things as we have gone down this road, where have we had the greatest inroads in using data to change decisions making in agriculture? I think an example of great penetration is the idea of using the ability to use scanners, for example, to identify off-color fruit and vegetables and decide whether this fruit is ripe or unripe or damaged. Those are simple real-time choices, and we have made great inroads there. It is harder, however, to address more complex choices. And using all of this data that we're talking about to decide whether you're going to plant corn or soybeans next year is a far, far more complex choice. And I think those are the kind of things that we are going to be challenged with to accomplish in the future. I think one of the other things, because in my work and risk in my career and thinking probabilistically, our models, it's not good enough for them to predict. They must be superior to a well-informed decision maker. And farmers or managers of a fruit processing facility, they know a lot just from their experience and things like that. And if we're really going to get penetration in using some of this technology, we're going to have to find a way to offer the manager or the farmer knowledge that is better than what they know subjectively. And one of the things that I think as people get excited about this, omitted key variables are still a real problem. I'll use an example. Yield monitor data on combines is very readily available today. Data from the planter that planted the crop or the fertilizer application. But a relevant question may be, well, why did the farmer put on this level of nitrogen fertilizer? Well, price may have been a part of that question. And we ultimately end up in all these scenarios where there is omitted variables, which with all the excitement over AI and so forth, omitted variables in my mind are still a problem. Next slide. Or is that my last? No, my last one. And I'm sorry, Jane, this has got, if you'll punch it a few more times, there's some boxes in this one. But ultimately, there are kind of four sources of data that I think we need to think about. Research and experimental data at our universities, for example. Program and administrative data that may be collected by the federal government as they interact with production agriculture. Private data that is held not by the farmer as much as it is an entity, a company that interacts with the farmer, or weather data, for example, that comes from one part of government but not another. And ultimately, in this ecosystem of data of the future, I think one of the things that we need to think about is the omitted variable problem. That's item number 4 in this Venn diagram, that would collect, if we step back from the data and say, okay, what really drives this decision, and collects surveys that both provide benchmarks with randomized control survey procedures, as I mentioned earlier, and things like prices or farm financial information that is not being generated in the data system. So this is kind of my picture of what, if in 10 years we do everything right and we kind of build a data system that really works for research, this would be an example of some of the things that we would have to do. So Jane, I thank you. I think this is my last slide. And
Yes, thank you, Dr. Keith Coble.
Okay.
For that very interesting introduction to big data and the uses and the issues along the supply chain. Next, we'll be hearing from Neha Jain.
Thanks so much for the invitation to speak here today. So I wanted to present some of my lab's work using satellite data to map different agricultural characteristics. And today I'll focus on a specific use study mapping cover crops in the US Midwest. So cover crops are crops that are grown on farm to maintain soil to maintain soil cover in between growing more productive crops like maize, like corn and soy. Next slide, please. So satellite data can provide valuable information on crop management practices and their outcomes at scale. And why is this important? Next slide, please. Historically, this information has been collected through things like household surveys, which are incredibly valuable, but are very time and cost intensive to collect and really difficult to scale across large areas and through time. Next slide, please. Another source of data are census statistics, which are often derived from such household level surveys. And these are also really valuable, but you might have some constraints. So first is potentially their resolution. So oftentimes these census data are produced at, say, the county or state scale. You're not really able to get this field level information. And it also might be some data set that's produced every, say, 5 to 10 years and not seasonally. Next slide, please. And this is where I think satellite data can really come in to help create this high spatiotemporal data set. So remote sensing, this is just the use of Earth observation satellites that are in orbit, looking at the planet, taking pictures every single day of the Earth. We as remote sensing scientists are coming up with algorithms that can translate the pictures that these satellites are taking of fields and different land covers on the ground to actual meaningful information that we care about. Next slide, please. So currently we're in a golden age of satellite data and also cloud computing. So this is just a picture showing some of the many satellites that are currently up in orbit or about to be in orbit through NASA. You also have satellites that are being put up by different other agencies like the European Space Agency, Indian Space Agency, et cetera. There are dozens and dozens of Earth observation satellites out there. And as you can imagine, these satellites are collecting large volumes of data. So in parallel, what's really been able to propel our remote sensing field forward is this growth in our ability to process high volumes of data through cloud computing. So in particular, there's a platform called Google Earth Engine, hosted by Google, that allows us to do really large scale analyses on the cloud at scale. Next slide, please. And these data are really powerful. So in my lab specifically, we've been able to map all of these different farm level characteristics that I list here. I won't go through every single one, but not only are we able to map all of these different variables, we also are able to do these at pretty fine spatial resolution. So ranging from 3 to 10 meters squared, which means that, this is at the field, at the subfield level. And it's also something that we can once again produce seasonally and also in real time. So these data can be really, really powerful. Next slide, please. So today, just to highlight one use case of satellite data, I'm going to talk about some work that I'm doing in collaboration with Jennifer Blesch, who's an associate professor at the University of Michigan. And we're using satellite data to map the adoption of cover crops at the field level across Michigan. So this is some work that has been funded by the USDA. Next slide, please. So specifically what we did was we used Landsat satellite data. So this is a satellite that is currently in orbit from NASA at 30-meter resolution. And we used this satellite to map various types of land cover during the winter season, including cover crops. So this is just a map of the area under different land cover types that we found from our satellite image analysis. And specifically the areas that we care about for cover crops is the dashed line, the dark green dashed line at the bottom of the legend called high cover. And we can see that it's fluctuating through time and potentially even increasing in more recent years. And I won't go through the methods given this short presentation of how we actually derived these different land covers, but I would be more than happy to discuss this during the Q&A. In general, what we do is the satellites measure different wavelengths of light that are being reflected back to the satellite from Earth, and we can then come up with algorithms that translate those wavelengths of light into different land covers or different measures of vegetation. Next slide, please. And then what we were able to do, since we had area under cover crops at the field level at 30-meter resolution, and from 2009 to 2018, we were able to look at trends in cover crop adoption through time. And what we found here is just a map of Michigan with various counties highlighted, with all of the counties highlighted in black lines. In orange are counties where we saw cover crop area was actually decreasing through time. In blue are areas where cover crops were increasing through time, and in gray are areas where we didn't see a statistical difference. And you can see sort of a spatial patterning in our results where we're seeing some increases in cover crop adoption, particularly in the southern part of the state. Next slide, please. Next, what we wanted to do is we wanted to understand what are some potential drivers of these changes in cover crop area through time. And specifically, we were interested in looking at EQIP. So this is, for those of you who are not familiar, this is the, sorry, I just want to make sure I get the acronym correct, the Environmental Quality Incentives Program, which provides financial and technical assistance to agricultural producers to address natural resource concerns. And they specifically have funds earmarked for cover crops and promoting cover crop adoption. So what we did here was we ran 4 panel fixed effects regressions. So these are regressions that are controlling for both county and also year as fixed effects. And this helps us better causally identify the relationship between dollars and EQIP or area under EQIP cover crops and the actual adoption of cover crops in that same year. And what we find, the first 2 columns, you can look at that first row, payments for EQIP and USD. And what we find is that as more dollars are given for cover crops under EQIP, we are seeing an increase in cover crop adoption. So we are seeing that, dollars are actually having their intended effect. And then the last 2 columns, here what we did was we instead looked at the planned area under cover crops under EQIP, which is just another measure of the amount of investment from the government. And we find also, once again, that there's a strong positive relationship where with more planned area under cover crops, you have more adoption. So, these results aren't surprising, but they are showing that the policy is actually effective and pretty effective to a high degree. Next slide, please. So what we're finding in our work is not only can we use satellite data to just map the general presence of any cover crop, we can actually use it to map individual cover crop species as well. And the reason that this is really exciting is because different cover crops can have different ecosystem services or different benefits in field, depending on the type of crop that it is. So specifically in this project, we tried to see whether we could map ryegrass versus red clover, which are 2 different types of cover crops that represent 2 different functional niches of cover crops. Next slide, please. So here what we did was we used Sentinel-2 satellite data. So this is another satellite data product that is produced and hosted by the European Space Agency. And this is at a 10-meter resolution. And what we did was we went on the ground in Michigan and we collected data from about 400 farms across the state where we measured different winter covers, including these different cover crop species. And for the sake of time, I won't go into the details of how we did this. Next slide, please. And what we find, so here, this is just a plot showing a measure of vegetation biomass that satellites can measure. This is called Normalized Difference Vegetation Index, or NDVI. You can just think of this as the amount of vegetation growing on the ground as seen by the satellite. And what we can see on the x-axis is time from the beginning of April till the end of August. And we have our different land covers that we collected data from in our land cover class, Legend. And what we can see is all of these different land cover types have different patterns of vegetation biomass growth through time. And what we can do is we can then develop an algorithm or input these data. Specifically, what we did was we input these data into a random forest model, and we're able to actually use the information from the satellite to predict these different land cover classes. Next slide, please. This is just a result showing the overall accuracy of our land cover classes. These are called F1 scores. You can think of this as 1 is perfect prediction, 0 is poor prediction, and we're getting pretty good predictions. I would say in remote sensing, getting predictions of the range of 0.7 to 0.9 are pretty good. And you can see, especially if we focus on the 2 cover crops, clover and rye, we're getting prediction accuracies, F1 scores of 0.7 to 0.77. So this is pretty good. And this is better than current existing products. For example, the USDA produces its own cropland map using satellite data called the NAS cropland data layer, and they have very poor prediction accuracies for cover crop species. So we found that our model did improve on these previous estimates. Next slide, please. So in sum, satellite data can be used to map a variety of different agricultural characteristics at the field scale and seasonally. And in this case, we specifically used it to map cover crops. Next slide, please. These data can be used to identify trends and also the drivers of adoption. Next slide, please. We found that cover crop area was increasing in several counties in southern Michigan. Next slide, please. And EQIP is very successful. So the more dollars or area invested in cover crops, the more cover crop area we do see. Next slide, please. Thanks so much. If you have any questions, I'd be happy to answer them at the end of this talk, or please email me. Thanks.
Thank you, Meha. Who knew that you could identify red clover from outer space? It's fascinating, just fascinating. Thank you very much for that presentation. Now we're going to turn to Yujing Zhang, who is going to present some consumer side instead of production side of the agricultural marketplace. Welcome, Yujing.
Next slide, please. Okay. Thanks for having me here. Today I'm going to be talking about big data for consumer studies with a focus on the scanner data. Next slide, please. A few words on my research program. Basically, it's about the food as a medicine. So I work on consumer studies, products such as alternative plant-based meat alternative, and also hemp, and also work a little bit on producer side as well, such as labeling and certification, more recently on the connection between food and health. But next slide, please. So let me first talk a little bit about some data that are suitable for consumer studies, but they're not so big. So in general, they are less than 500,000 observations. So I list 4 here. The first one is the current population survey. So it's CPS, Food Security Supplement. It has a lot of good measures such as food security. So it's good for studies such as how the grocery tax affects food security. So the second data set here I outline here is a PSID panel study of income dynamics. It has a lot of good information on health, family. It's good, for example, grocery tax on obesity. In particular, this panel has linkage between generations of households. So if you're into generational household food behavior, this could be really good fit. The third one is food apps data. The nice thing about this data is it has not only the grocery food purchase, but also on restaurant and the school acquisition as well. But the downside about this survey is only 1 year. So it's 2013, and USDA is planning to do 1 additional year. The last one is Enhance. So it has different years of waves of data available collected by the CDC. It's good in the sense it has very accurate measure of some biomarkers, such as blood pressure and etc. But for the food part, it's recall, so it's not accurate to collection of the data over the transaction part. So next slide, please. So these are the scanner data, and I want to talk a little bit more in detail. So basically, we have 2 pieces of scanner data available to researchers out there. The first one is the Nielsen academic version. It is made available through the University of Chicago Booth Q Center. So it's also called a Nielsen IQ. So it has 2 parts. So the first one is consumer panel. I will talk a little bit in detail later. Retail scanner data, that's the second part. The third part is it's just made available starting from this year to the researchers. So it is annual ailment, health, and wellness survey data. So it records consumers, for example, do you have high blood pressure? Do you have mental stress, etc. So it's based on the annual interval. And this is made available to the university by institutional access. The second part of the scanner data is RI scanner data. They are comparable to the Nielsen data. So they have National Consumer Panel, it's called NCP, and also the RI InfoScan retailer scanner data. It has a recent name, it's called RI Omni Market Call Outlets. And actually more recently, RI changed its name to Circana. So it's a different name now, Circana. RI has also the consumer health information. It's called MedProfile. So this is very comparable to the Nielsen annual ailment, health, and wellness survey. So In addition, I also provide drug prescription for select households. So that is very, very good data out there. Where they go to for the pharmacy, what kind of drug they get prescription filled, etc. And again, it is more occurred as less frequent level at the purchase data. So one unique thing about RI data is through USDA work, it's linked to nutrition database. So it's made possible through the purchase to plate crosswork. So for example, you actually, based on what consumers purchase, you can calculate a healthy eating index for the household on a dynamic window basis. So this healthy eating index could be updated on weekly or monthly or yearly basis. That's very nice feature for the RI scanner data. So to access RI scanner data, you will need to have USDA ERS collaborator. And as Keith mentioned, this is stored on enclave, so you cannot download the data to your local hard drive. For both Nielsen data and RI data, they have 2-year lag. So basically, the most recent version you can have technically for now is 2021, but recently they have done a much better job. I know RI data actually now they have the 2022 data available now. So next slide, please. So I'm just using the Nielsen data, for example. For the consumer panel data, basically you have thousands of households and you record what they purchase real time. Okay. For the retailer scanner data, basically record 35,000 participating retailers' sales for every universal product code level product at the weekly level. So you can see the difference. The first one is more on household purchase for smaller number of observation, but the retailer data actually is way bigger than the household panel. Next slide, please. So for the consumer panel data, not only record what purchase the consumers made during a shopping trip to a retailer, they also record, for example, where they live, their consumer demographic, who they are, the income level, race, gender, etc. So next slide, please. For the retailer panel or retailer scanner data, and actually I mentioned a little bit, they have better coverage in terms of products. For example, if you want to study some very infrequently purchased product, for example, e-cigarettes, then if you focus on the household panel, you will not have a lot of observations over a year. But if you use the retailer panel, you will have, at least maybe 500,000 observations for several years. That's one difference, I think, if you want to look into which data you want to use. So in terms of years available for a consumer panel, it started in 2004. For the retailer panel, it started in 2006. So for the RI data, it has a very similar window, but usually the most recent data starts from 2012. Next slide, please. I want to talk a little about the data hierarchy right here. For Nielsen data, it's organized from top to bottom by departments, product groups, and product module. So you can see, for example, chewing gum goes all the way from dry grocery to gum to sugar-free chewing gum, and then go to the product detailed product UPC. So next slide, please. For RI data, they actually has very different data structure. I'm going to use one different example. So the top actually is department. Then you go down to aisle, category, product, and UPC. For example, for the products we have been starting here is hemp products. A hemp granola snack bar will be in the general food department, snack aisle, snack granola bars category, and finally granola bar product. So here I'm going to use one example to highlight what you can do. But in general, what you can do for this scan data first is demand analysis. So you can analyze, for example, product entry using a Hurdle model, a Heckman model, or Tobin model, for example, demand for bourbon whiskey in Kentucky. You can use those kind of model. You can also use, well, a demand assistant to estimate those kind of products. The second type of analysis actually is, well, a choice model. So for example, you want to analyze consumers' choice for different types, brands of coffee products. So to be able to estimate a model like that, not only you need the price data for the product you purchase, you also need the information for the competing product, right? So the prices for the available product choices after that. That is the key defining characteristic of scanner data, because the retailer data has those price information for you. So a choice model, you can also do that for the consumer and also retailer panel data. So finally, we can also do a lot of policy analysis using kind of DID type analysis. So this is one example we have been working, previous slide, please. We have been working with University of Vermont, Arkansas, Western Colorado Western Colorado University on consumers' preference for hemp product, especially how hemp and the marijuana policy is going to affect the consumer demand for hemp and the CBD products. So that's kind of like give you a sense what the scanner data are capable of doing. I'll stop right here, and I'll be happy to take questions.